Welcome back. Today we are going to discuss a very important thermodynamic quantity, that is equilibrium constant. In classical thermodynamics, we have already discussed equilibrium constant at length and connected with the change in standard molar Gibbs energy. In statistical thermodynamics considerations, we are going to connect this equilibrium constant with molecular partition function. The experimental measurement of equilibrium constant can be done in a variety of methods. There can be spectroscopic methods, there can be calorimetric methods, there can be direct methods where a suitable fitting of the model to the experimental data points can give the value of equilibrium constant. Alternatively, we can get the value of equilibrium constant from the value of delta G naught, and delta G naught is equal to delta H naught minus T delta S naught. So, therefore, there are variety of methods, calorimetric, spectroscopic, and there may be some other methods which you can use for experimental determination of equilibrium constant. Even when we talk about the spectroscopic determination of equilibrium constant, and then those who have consulted the book by Lefkowitz and are dealing with the interaction between ligands and biological macromolecules like proteins, then Stern-Volmer kind of analysis can give you the value of quenching constant, which under certain circumstances can become equal to equilibrium constant. In this course, we have been talking about the molecular partition function, and by now we have discussed all contributions to the molecular partition function. For example, translational contribution, rotational contribution, vibrational contribution, electronic contribution. These are the four major contributions that form the overall molecular partition function and which can be related to various thermodynamic quantities. In today's lecture, as I just said, we are going to connect the equilibrium constant with the partition function Q. What is the significance of equilibrium constant? Just as a recap to earlier knowledge. Equilibrium constant is a very important thermodynamic quantity because it tells you how much product is formed. Equilibrium constant is the ratio of the concentrations of the product to that of the concentrations of the reactants weighted by the power of their respective stoichiometric numbers. In industry, equilibrium constant is very important because, as I just said, equilibrium constant is directly related to the amount of product formed. And therefore, in industry, they are always in finding out appropriate conditions which can be tuned to achieve a desired value of equilibrium constant. And the molecular partition function, since we have discussed that it is connected to the energy levels of the molecule, and therefore, that means here also the determination of equilibrium constant by statistical means is in fact spectroscopic method of evaluating the value of equilibrium constant. Let us begin our discussion. There are two things I want to highlight to begin with. One is that we will discuss ideal systems first, ideal gases. So, therefore, initially I will restrict to gas phase reaction, and also the gas phase reactions means I will talk about ideal gases. Non-ideality we will bring later. Equilibrium constant K is related to delta G naught by this equation, delta G naught is equal to minus RT log K. In classical thermodynamics, we derived this equation delta G naught is equal to minus RT log K based upon a certain derivation which was delta G is equal to delta G naught plus RT log Q. In this equation, delta G is the change in Gibbs free energy. Delta G naught is the change in Gibbs free energy under standard state conditions. Remember difference between delta G and delta G naught. It is a common mistake. Sometimes we do not differentiate between the two, but these two convey entirely different meaning. This delta G is actually the slope delta G delta xi at constant temperature and pressure. That means the positive or negative value of this delta G is going to decide in which direction the reaction is spontaneous. At equilibrium, delta G is always 0. This slope is 0 and Q is equal to K. So therefore, when you rearrange that, you get delta G naught is equal to minus RT log K. The purpose of this discussion was to again highlight the difference between delta G and delta G naught. These two are not the same quantities, these two are different quantities. Now, since today's task is to correlate K with Q, that means we have to connect this K somehow with the Gibbs free energy or the changes in Gibbs free energy under standard state conditions. From our previous discussion, we have derived this equation G is equal to G0, this is absolute 0, T is equal to 0, is equal to minus nRT log Q by N. This we have discussed earlier. And we had also discussed that N, number of molecules, is number of moles times Avogadro constant. So therefore, when you convert this upper equation, this equation, and write N is equal to small n times Na, then Q divided by N becomes Qm, molar partition function, and throughout you divide by N. If this equation is divided throughout by N, it results into this equation, where N is consumed into per molar quantity. That means what I am writing here is G by N is equal to Gm, molar quantity. And we have invoked standard state conditions. You see throughout this naught has been put. Why I am putting these standard state conditions? Because the relationship that I am interested in connecting is delta G naught is equal to minus RT log K. So therefore, I need to have expressions for Gibbs free energy under standard state conditions. Okay, so from here onwards, we will talk for the Gibbs free energy under standard state conditions. So what is a standard state? First of all, we should be clear on what is a standard state. We have also discussed, or your teachers might have already discussed with you, what is a standard state. Usually, the answer comes temperature 25 degrees centigrade. No, temperature can be any, substance should be in its pure form, and pressure should be 1 bar. That is, the latest recommendations of IUPAC. What is a standard state? The substance should be pure in its pure form. Pressure should be 1 bar. This is very important. Pressure should be 1 bar. Temperature can be any. There is no fixation of temperature. You can have standard state conditions at any temperature. For example, you have nitrogen, N2. The standard state of nitrogen N2 is gas at 25 degrees centigrade. If you reduce the temperature towards 0 Kelvin, the standard state will be different. So therefore, temperature can be any, substance should be in its pure form, and pressure should be 1 bar. In other words, P naught, this naught here signifies the standard state conditions, that is 1 bar. And since here we are dealing with ideal cases, ideal gases, I will write PV is equal to nRT, that is a perfect gas equation or ideal gas equation. So that means here V, I can write this as V by N is equal to RT by P. And then after that, if I invoke standard state conditions, then V by N becomes Vm naught. And P, instead of P, I write P naught. What it suggests is that when you are dealing with the gaseous systems and treating the gases as ideal gases, then you can always calculate the volume by using RT by P naught. Volume need not be given to you. You should be able to calculate from the knowledge of gas constant and from the knowledge of temperature. P naught is anyway 1 bar. So therefore, under standard state conditions, it is easier to get Vm naught. No data needs to be given. It is very important to understand the concept of standard states. I hope this description of standard state is clear to you. Now let us express the molar Gibbs function under standard state conditions for any species J. Any species J. So Gm naught minus Gm naught at 0 is equal to minus RT log Qjm naught by Na. M stands for molar, J stands for species J, naught stands for standard state conditions, Na is the Avogadro constant. And as mentioned over here, Qjm is the standard state molar partition function of species J. Now consider any reaction, any gas phase reaction. One such example is A moles of A reacting with B moles of B to form C moles of C and D moles of D. This is the expression that we are going to use, this one. This expression allows me to express molar Gibbs function of J under standard state conditions in terms of molar Gibbs function of J at absolute 0 and the molecular partition function. What I am interested in is knowing delta G naught. And some books will write a subscript R. You can write R means reaction. So reaction Gibbs free energy change under standard state conditions can be obtained from summation J nu J Gm J under standard state condition. What it means? If I expand this for this reaction, let me put a partition over here. That means for this reaction, the way I will expand this expression is, in this, let me explain various notations. R stands for reaction. This symbol stands for standard state condition. Nu J is the stoichiometric number which is positive for products and negative for reactants. I repeat, nu J is the stoichiometric number which is positive for products and negative for reactants. Use this positive for products, that means what I will write is equal to, I open this summation, this will be C times GM naught C plus D times GM naught D minus A times GM naught A minus B times GM naught B. When I said positive for products and negative for reactants, that stoichiometric number, it is becoming clearly here. I am writing C and D both has positive numbers, they are products. A and B, they are negative numbers here, written over here, these are the reactants. Okay. What I will do is now, let us go step by step. I am interested in finding this expression. Summation J nu J, I will retain nu J over here, and in bracket I will use this expression over here. This is equal to GM naught J at absolute 0 minus RT log QJM naught by NA. We have simply substituted for GM naught. This means I can now write delta R G naught is equal to summation J nu J GM naught J at absolute 0 minus RT is common constant, it comes out. So this one J nu J log QJM naught by NA. Try to understand it. What is simply done is, we use this equation which says that reaction Gibbs free energy under standard state conditions can be obtained from the standard state Gibbs function of the products and reactants, weighted by their stoichiometric number. And what I did was, then I retained nu J of this, and for GMJ I substituted this, and we arrive at the next equation, which is equal to delta R G naught is equal to this summation at absolute 0 minus RT into this expression nu J log QJM naught by NA. We will continue from here. So what we have is delta R G naught is equal to summation J nu J GM J0. This is my first expression from the previous equation. This one minus RT log minus RT summation J nu J log Q M J naught by NA. Purely general equation. This is what we had, minus RT nu J log Q J M naught by NA. Okay. Now, if you very carefully look at this, this is also delta G naught at absolute 0. So that means I have under general conditions delta G naught is equal to, this is delta G naught for J at absolute 0 minus RT, and then allow me to write next expression like this. What I have done is I have taken this stoichiometric number as power. It's permitted mathematically. Okay. Now we need to write something for this. Consider G is equal to H minus Ts is equal to H is equal to U plus PV minus Ts, and since we are dealing with ideal gases, which is U plus nRT minus Ts, and doesn't this equation says G at absolute 0 is equal to U at absolute 0, because when T is equal to 0 then G becomes U. Now I can write next one, delta R G naught is equal to delta U, I will say J at 0 minus RT summation. When you open the summation, this is log A plus log B plus log B plus log C, right? And when you say log A plus log B plus log C, etc., that will be equal to log A into B into C, etc., etc. I can convert this summation into product. So I can write this as a product. That means this will be minus RT log product of QJM naught by Na raised to the power nu j. So M and J are getting interchanged, don't worry about that. So log product of all this is equal to log A plus log B plus log C, etc. So I have used that mathematical transformation. I hope by now it is clear how we got this expression. What we will do is that instead of delta U, we will write this as delta E 0. Just a symbol to describe that this is the difference in the 0 point energies. Instead of delta U, U shows internal energy, we will just rewrite in the term delta E naught. Okay. So the new expression that we get now is delta R G naught is equal to delta E naught minus RT log pi j Q J M naught by Na raised to the power stoichiometric number. So by now we have an expression for delta G naught, and we have some right hand side which is expressed in terms of change in 0-point energies and the molecular partition functions. That means the right hand side of this equation can now spectroscopically be determined. So, what we have? Other equations that we have with us are delta G naught is equal to minus RT log K. This expression, this equation we have derived when you were learning in classical thermodynamics. R is a matter of convenience, usually R is written for reaction. Now you see, this delta G naught and this delta G naught can be equated, and once you have these two equations, we can come up with an expression for equilibrium constant. So you might have noted the strategy. Since we wanted to develop a connection between equilibrium constant and molecular partition function, and we realized that the equilibrium constant can easily be expressed in terms of changes in standard molar Gibbs energy. So we decided to express Gibbs energy in terms of molecular partition function. Then through a series of steps, we have come up to this expression where the right hand side can be spectroscopically determined. The next step will be to equate these two and then come up with an expression for equilibrium constant. But that we will discuss in the next lecture. Thank you very much.